Okay. Yeah, I'll go ahead and get started. Thanks everybody for coming out. For those who are not familiar, the Habitat Rearrangement Challenge was a challenge hosted in the competitions track at NeurIPS 2022. The submission started, the leaderboard opened around the beginning of August and ended on November 1st. So I guess before I get any further into it, let me first talk about what will happen at this actual workshop. So here is an overview of the schedule for today. And the schedule is also posted on our website. So if you go to the NeurIPS page for this, you can find our linked website, and then the schedule is also there. So if you ever want to refer to that as well. So in this first 15 minutes, I'll give a brief overview of the challenge, some general findings and some trends we found in the challenge. Then we'll hear from some of the winning teams of the Rearrangement Challenge. And in this and all the other presentations, there'll be time to ask questions from the speakers as well. And the workshop will be recorded, and we'll make this available afterwards. Then after that, we'll hear from some invited speakers about related work and related research. And then finally, we'll hear about the results of the 2022 Object Nav Challenge, which was a concurrent challenge focused on the Object Nav problem. But to start off with, I'll give a brief overview of what the Habitat Rearrangement Challenge is and what we saw in the challenge. So at a high level, the goal of this challenge is to control a home assistant robot to rearrange one object from a start to a goal position. Specifically, the task goal is provided to the robot by a start coordinate of where the object starts and a goal coordinate of where that object should go. And the key thing about this challenge is there is no privileged information provided to the robot. The robot is placed in a new home and has to do this without any pre-built maps, 3D models of objects, knowledge of obstacles, or so on. The robot has to entirely operate from onboard sensing. So in this competition, we had two different challenge tracks. The first was rearrange easy, and then the harder rearrange. Participants could separately submit to both, and I'll talk about what the differences are. So in the rearrange easy track, the key feature is the object starts on an open receptacle. And this means the robot does not need to open any containers to access the object. So for instance, on the left-hand side, and the right too, the robot can just grab the object. And then the same is true for where the robot needs to place the object. The goal of the object is also on free space in a open receptacle. And this means the robot can always execute the same sequence of navigate to the object, pick up the object, navigate to the goal, place it at the goal. And also a part of this competition, we included a harder rearrange challenge track. And the key difference with this track is that the object could start in an open or closed receptacle. So the example on the left-hand side, the robot first needs to open up the drawer to access the object inside. And so this adds the challenge that now the robot needs to infer if it first needs to open up a receptacle such as the drawer or the fridge before accessing the goal or the object. The agent in both of these tasks is a simulated fetch robot. The fetch robot is equipped with a mobile base, 7-degree of freedom arm, and a suction gripper. The base is controlled by specifying a linear and angular velocity, and then the arm is controlled by specifying desired positions for the joints. And then with a suction grasp, the robot is able to lift objects when the suction gripper makes contact with an object and the suction is turned on. And then the agent observes the world through a head-mounted camera that produces 256 by 256 RGB and depth images. The agent is also equipped with some proprioceptive sensing, meaning that it has base ego motion that tells it where it is relative to the start of the episode. And it also has a knowledge about its current joint angles of the arm. So participants in this challenge were tasked with designing an algorithm that takes as input these observations and then produces control for the base and the arm. And then one more thing is there's also this stop action, which needs to be called when the objects are successfully rearranged. and the stop action ends the episode. So we evaluate approaches by 3 criteria. The primary criteria is the success rate, which is the ratio of episodes the agent actually moves the object to within some threshold of the goal. And for this challenge, we define that as 15 centimeters. And then we also have another metric for partial success, which is the distance between the object and the target. And then we also have a way of measuring efficiency by the average time it takes for the robot to solve these episodes. And then if the robot does not solve the episode within some maximum time budget, this counts as a failure. So in terms of assets, we evaluate all the algorithms in the replica CAD scene data set from the previous Habitat 2.0 work. This is a fully interactive space, so the robot can open things up, pick up objects, drop things. And we also have a focus on generalization to new spaces. So we have macro variations of different layouts of furniture within this apartment space. So for instance, the kitchen might be in a totally different location. And then we also have these micro variations where it's the same general layout, but the furniture is slightly perturbed. The position and rotation of furniture. So in this challenge, we reserve 3 of these distinct furniture layouts for a training data set we provide to participants. And then each of these macro variations has 20 associated micro variations as well. And then we also provide a validation data set to participants as well. And then we hold out one of these variations for the final test set. So as will be described later, this test set is only on eval.ai and participants do not have access to it. So therefore, the agent will actually need to generalize to performing this task in different home layouts. Then we use the YCB object data set with the food and kitchen category for this task. And for the purposes of this challenge, the set of objects is the same between train, validation, and test. So we procedurally generate these object placements and generate 50,000 training episodes for the task and 1,000 validation episodes, which are provided to the participants. And then we also reserve 1,000 test episodes with these unseen layouts that the participants never see. So for this challenge, we have a starter code repo that has 2 extendable baselines from a monolithic end-to-end RL approach to a more modular task planning with individual skills approach. Participants then submitted their agent to eval.ai via some Docker file, and then eval.ai would return the result, and that's where the leaderboard was. So in total, we had 19 registered teams, 6 teams participating, and 35 submissions. I'll talk about a brief overview of the approaches, but the winning teams will go more into this. So the majority of the teams actually use some form of a modular approach. This modular approach broke down the task into individual skills, where each of these skills would be some goal-conditioned skill policy that was probably trained with some form of reinforcement learning. And then there would be a high-level policy or task planner that would then sequence these skills together to solve the task. And here's an example for the validation split of the rearrange easy task, where the bottom of the screen shows which skill is being currently executed. And you can see that it sequences together the skills to successfully complete the episode. We found that the monolithic RL was very unpopular. And by that, I mean a policy that goes directly from pixels to actions. So it directly takes the visual inputs as input and outputs all the actions for the robot. The challenge with this approach is that it's even after a ton of training at 200 million steps, while the robot could learn to do the first part of the task of picking up the object, it actually never learned to place the object. And the success rate was 0% with this end-to-end approach. And this is the baseline, again, on the rearrange easy track. And I'll give a brief overview of kind of some findings from across all the different methods. So here is a summary of the leaderboard for the rearrange easy task as the outcome of the challenge. Congrats to the multi-skill mobile manipulation team. And that'll be the first presentation after this for winning the challenge. getting 64% on the rearrange easy benchmark and 66% on the holdout challenge test split. We looked at the effect of the distance between the starting object and goal position against the success rate, and generally found that for the winning approach, the method performs better for objects that are closer to the goal. We also did a breakdown of the failures, the different failures for the top performing approach to kind of analyze what are the remaining problems. We found that the major failure case was due to this forced terminate condition where the robot hits against the scene too much or crashes too much, which causes the episode to terminate. So this is if the robot is not being careful enough, maybe it drops an object, maybe it crashes into something that's not allowed in the task, and the task will terminate with a failure. There's also this bad stop. Like I mentioned earlier, the robot needs to call the stop action when it's done with the episode. If it prematurely calls that stop action when the episode is not successful, then this is counted as a failure. And that's another major source of errors. And then finally, we have this timeout, which could be a number of different things where the robot is not able to complete the episode within the desired time, or maybe it gets stuck at a particular part of the task. And then next, we have the harder rearrange competition track. We saw less submissions here, but again, multi-skill mobile manipulation 1. This track is certainly harder than the previous track compared to the 64% success rate. And we're excited to see more progress on this competition track. And finally, I want to conclude by saying that despite the challenge being over, the leaderboard is actually still open, and we plan on keeping it open and maintaining it, fixing any future issues and keeping this as a centralized source of truth for any sort of embodied rearrangement agents in the future. So that will continue to be open and people can continue to submit to it. All right, I will stop there and then pass things over to our first team, which is the multi-skill mobile manipulation.
Okay. Hello, everyone. Let me know if you cannot see my screen.
We can see it.
Okay. Okay. Thanks. Yeah. And yeah. I'm Jiayuan. I'm very glad to introduce our solutions to this rearrangement challenge. Our solution is named as like M3 multi-skill mobile manipulation for object rearrangement. And our code and like the relevant paper is already released. So if you have interest, you can go and search and like check it. So first, for this kind of like long horizon tasks, we all know that it's quite like difficult. So we use this modular approach that we decompose the 4 tasks into like subtasks. So a skill is learned for each subtasks. However, at the core of this kind of method is subtask formulation. So we follow the TPSR baseline proposed in the original Habitat 2.0 paper. We like train a set of RL skills, which we use like PPO to solve these kind of subtasks. So we have like pick, place, navigate, open fridge, close fridge, open drawer, and close drawer skills. So here we show an examples that we show an example here. Okay, is it play? Sorry. Is this video play? If it's not play, maybe let me know. Sorry, I need to go back here. I hope it's played, but I think on my screen I cannot see it played. But okay, it's just showing some like cases that the 4 task is solved by the skill training. So we train the skills like sequentially executed and to solve the like long horizon tasks here. So for the subtask, here we use the skill training. So we use skill training as a criterion of the subtask formulation. since a good subtask should lead to like a reusable and tractable skills that can be chained with other skills. Excuse me, is my screen frozen or?
We see the slide titled subtask skill and skill chaining.
Oh, okay, great. Okay, and here we summarize like 3 principles to formulate like skills: achievability, composability, and the reusability. So each task like can be subtask can be evaluated by this criterion, like how well we formulate these skills. However, when I review the literature, I find that like most prior works in RL and robotics separate the mobile platform and the manipulator. So here, example, like prior methods chain the navigation skill and stationary manipulation skills. So the issue is that it will suffer from the compounding errors in skill chaining. Here is the example, like the robot fails to reach the target object if the robot is not close enough to the object. Our solution is to switch to mobile manipulation skills. Since we can see that the mobile manipulation skills can have like a larger initial states to contain the terminal states of the previous navigation skill. So here is an example. The mobility can compensate for the errors from the navigation skill. We also devise like an efficient pipeline to sample the initial states for mobile manipulation skills. Please refer to our paper for more details. Here is also another example, like we compare the initial states for mobile manipulation skills, which is on the left, and we also compare it with the stationary counterpart on the right. We can see the initial states of the mobile manipulation skills are much larger, which means it can have like better ability to compensate for the errors. And thanks to the flexibility of mobile manipulation skills, we devise a region goal navigation reward to facilitate learning navigation skills. The prior method used like point goal navigation rewards to tackle it. However, it ignores the existence of multiple good locations connecting navigation and manipulation. To this here we can see like point goal reward. We illustrate how we generate the single goal. So the single goal is like randomly sampled by rejection per episode, and it's visualized as like a green arrow on the floor. So let's see what's the issue for that for the point goal. First, let's see how we write this like point goal navigation reward. So usually point goal navigation reward consists of these components. First, the negative change of the geodesic distance to the point goal, and the negative change of the angular distance to the desired orientation when the robot is like close to the point goal. Besides, this reward also contain like the success reward and slack penalty. Here are the issues. First, the point goal can be like random per episode due to like sampling procedure. And the angular distance reward can encourage the robot to enter the region by like backing onto the target instead of like pointing toward it. Okay, then we know that like the point goal navigation reward we introduced can lead to like poor convergence and generalizability due to this kind of goal ambiguity. Our solution is to use a like region goal navigation reward to encourage the robot to reach like any of feasible goals in a region. Here is an illustration of the region goal. So we only encourage the robot to navigate to any feasible goal within that region. And the region of this case is visualized as like green points on the floor. For our region goal navigation reward, we make like several modifications. First, we compute the geodesic distance to a region of goals instead of a single point goal. The geodesic distance to a region goals is the minimum geodesic distance over all goals within the region. Second, we remove the angular distance and rely on the success reward only to encourage a good orientation. Third, we also add a collision penalty to filter like infeasible goals which are not collision free. Next, I will show some experimental results on the home assistant benchmark, which is proposed in the original Habitat 2 paper, which also similar to our challenge here, like rearrange easy and rearrange. Yeah. So we show some baseline comparison between the baselines and our method. The first baseline is like the stationary manipulation skills and the point goal navigation skill. So we can see it will get stuck and it get blocked by the TV since it navigates to a bad location. And in the second example, we can see if we use mobile manipulation skills, we can like avoid the obstacles and successfully like pick the objects. In the last example, which is our method, we can see that the region goal navigation reward can navigate to like a better or more suitable position for manipulation. Next, we show that the mobile manipulation skills can lead to like better manipulation location. For example, in the baseline, the target object is a sugar box, but it picks a wrong object since it gets too close to the wrong object. However, in our mobile manipulation skills, we can use mobility to adjust our position and pick a correct object. Here, we also show like our collision-aware navigation, as Andrew has introduced that like a major failure case may result from the collision. So here we add some collision penalty, and you can see that comparing like the baselines and our method can try to avoid disturbing the environment. For example, like closing the fridge door. In this case, we can have like a better success rate. Okay, and since our like region goal eliminates the ambiguity caused by the point goal, our region goal navigation skill also shows better convergence. Our results are shown on the right. So here's some takeaway. To summarize, we propose to use mobile manipulation skills and the region goal navigation rewards rather than stationary manipulation skills and the point goal navigation reward. So mobile manipulation skills can compensate for the imperfect navigation, find a better location for manipulation, reduce heuristics to design feasible initial states. The region goal navigation reward can lead to less memorization and better generalization. It also reduces heuristics to design feasible point goals. And for the challenge, we also do some modifications to adapt to the like new settings, but the main idea is almost here, same here. Yeah. Here are some like future works we may pursue. For example, we can introduce like feasibility, like SECAN for the skill training. We can also investigate like more skills, like many skill 2 benchmark. And yeah, here I give the acknowledgement to my collaborators. Thanks for their advice and suggestions. And now it's like maybe time for the QA. Yeah. Thanks.
Thank you. Yeah, if anyone has any question, yeah, feel free to just unmute and directly ask. Maybe I can start then. A question that I have is, do you have any thoughts about approaching tasks that are like rearranged, where you don't know the order of skills, or there might be some like variable ordering of skills in your approach?
Oh yeah, I mean, currently we follow the original paper that we task planning to generate this kind of sequence, but like how to generate a sequence maybe on the fly, like according to the current situation. Yeah, it is a like very great question. Yeah, I saw some works maybe from Fei Li's group, like Stanford's group. They try to combine like a feasibility, integrate the feasibility prediction into the like task and the motion planning, so that they can try to like search a solution like based on the maybe online like planning. So I think it's a like direction for this like rearrangement challenge, like how people can try to integrate this system. I think before like since before the deep learning era, like people do not really have this technique can combine these things. Like they cannot really predict the feasibility. But I think in the recent work, we saw that like visibility now is able to be predicted like by the larger like vision, maybe language model together. So I think it's a future direction I also would like to pursue. Yeah.
No other questions from people. I have another one. Okay. In terms of your skill chaining, are there weaknesses still even with your training method where you notice problems with kind of the handoff between skills? Do you think your method has like completely eliminated any errors from the skill transitions, or do you still notice kind of limitations of your method where there's certain errors in this handoff that still happen?
Yeah. Yeah, thanks for this greater question. I think, yeah, it's definitely there exists some like corner cases. For example, currently like the mobile management skills can still not handle like long-term navigation. I mean, if it requires the tower, if it's like blocked by some obstacles, it cannot really like the tower very well. So it's a question that like how we can like I mean improve maybe the navigation ability a little bit in the mobile manipulation skills as well. Like currently, I mean the reason why maybe I need like both the navigation skill and the manipulation skills is that the navigation in this kind of household like environments require the tower ability. So it's something I need. I mean, for the navigation skill. Otherwise, I mean, definitely I can directly use the mobile management skills for all the tasks so that I can get rid of like one skill to train. But in this kind of challenge, I think currently it's still a challenge for this kind of like methods. So I hope that maybe later, if we can smoothly like train these skills, I mean, like using the interaction to adjust how these skills are trained, maybe it's possible that yeah, I mean maybe it's possible to solve the issue that I mentioned before, like for this kind of corner case. Yeah, thanks. Yeah.
Thank you. Yeah, thanks so much. We should probably move on to the next presenter now, which is team UESTC 529. So go ahead and share their screen now. Oh, I think you're still muted, by the way. But we can see your screen. I think you're still muted. Oh, there we go.
Okay. Sorry.
Oh, no worries. Yeah, we can hear you now.
Can you hear me?
Yeah, we can hear you.
Okay. Hello everyone, my name is Xuan Lao from University of Electronic Science and Technology of China. It's my pleasure to attend today's meeting. I will present our work, pre-trained visual representation for object rearrangement. This work could not have been completed without Deyao Zhu's collaboration. First, I would like to simply introduce the task. In the rearrange easy task, a fetch robot is randomly spawned in an unknown environment and asked to rearrange one object from an initial to desired position. All containers such as the fridge, cabinets, and drawers start open meaning the agent never needs to open containers to access the object or goals. The task planning is static with the same sequence of navigating to the object, picking the object, navigating to the goal, and then placing the object at the goal. An episode is successful if the target is within 15 centimeters of its desired position without considering orientation. As shown in here, our framework consists of two components. The left part is an encoder module, which encodes the RGBD images and other state information. The right part is an LSTM-based policy network. Next, I will introduce the two parts respectively. First, like the baselines, the ResNet is used to encode the depth image, but we don't discard the RGB image. We encode RGB image using R3M's frozen visual representation model presented by Neil et al. It has been validated to be effective in downstream robot manipulation tasks. Moreover, we also try to utilize other visual representation models, such as Clip VIP, which are presented by Redford et al. and Jason et al. Respectively. But we find that R3M performs better than the other two models according to our experiments. Then we concate the depth filter and RGB filter to obtain the RGBD filter. As for state encoder, we use an MLP to filter some other information, such as robot state initial position into a state filter. Finally, the RGBD and state filter are concatenated as the input of the LSTM-based policy network. Following the DDPPO framework, a distributed reinforcement learning approach, we use the LSTM network as our policy network. The concatenation of the future and the previous action is fed into the LSTM network to obtain the action of current time step. The PPO loss is used to train the policy network. Then we use the default hierarchical reinforcement learning method, TPSRL, to break down a task into a sequence of skills by a static task planner. DDPPO is used to train the navigation, pick, and place skills respectively. These skills are subsequently used to accomplish the task. Finally, we show the result based on the task standard leaderboard. We achieved third in the competition with a success rate of 0.21, a distance 2.83 meters from the target position, and 292 steps taken. Thanks for your listening.
Thank you. Yeah, again, anyone can unmute and ask a question.
When you were using these encoders, were they like Clip and R3M? Did you keep them frozen, or were you fine tuning them, creating the dates?
I use the frozen visual representation model of R3M. We don't try to fine tune them, just in our experiment.
I see.
So it's interesting that you guys compared all these different visual encoders. what sort of different did you notice like any sort of different behaviors or failure cases of the different encoders, and like what sort of gaps in performance did you observe between them?
Through our experiment, R3M's visual representation model can achieve the similar effect as the baselines on the training set. But R3M's performs better than the other two models. We verified the effectiveness of our method by replacing the technology corresponding to the basic method, and find that replacing only the picking skills can achieve a success rate of 0.3 on the validation set, but clip and VIP just achieve a success rate of 0.2 success rate.
Yeah, interesting. Thank you. It's interesting. The one you guys used generalizes so much better.
Okay, thank you.
Okay, yeah, if there's no other questions, then I guess firstly, are there any other questions before I move on? Okay, if not, we can move on to the next team. Thank you for the presentation.
Okay, thanks.
Hi everyone. So I'll be talking about our submission to the challenge. Yeah, we follow a similar approach like other teams, where we have a modular approach that chains skills trained using reinforcement learning. We try to use more mobile skills for better flexibility, where the agent is allowed to move both base and arm for the pick and place skills. And for this, we position the agent. For training these skills, we spawn the agent at 2 meters distance from the pick from the position from where the agent is required to pick the object, or where the agent is supposed to place the object. And we use the same nav which comes as part of the baseline, and we consider the skill to be successful if the agent reaches within 1.5 meters the target position. All skills were trained using VER, which is a recent technique proposed for training on parallel environments with higher sample efficiency, and we train with 64 parallel environments. These are the individual skill successes that we see. All skills reach above 80% success when evaluated individually. One consistent mode of failure which we observed was, you can see that as the agent, once it reaches the position, it just drops off the object without reaching close enough to the receptacle. So we observed this mode of failure to be consistent, and yeah, so this what was happening. So the agent, this is the object, and this is the goal position where the agent is supposed to drop the object. The old reward for place was based on object to goal distance, so there was no incentive for the agent to come closer to the receptacle before dropping it. before dropping the object. So we tried a reward where we reward the agent for reaching close to the receptacle before placing the object. That corresponds to this reward, where the reward is based on the distance between the end effector and the goal position. We found that this takes the agent's end effector closer to the goal before the agent places the object. So as you can see, with the old reward, the agent was on average reaching the end effector was reaching 1 meter from the goal before the agent placed the object. But with this new reward, it reached closer, and it also translated to better success. And this formed our submission. So this is a successful episode. As you can see, even though it has to place it at a higher, a more complicated position, it does it well. It takes the end effector all the way to the goal position and then places it. Similarly, this is another successful episode. The failure cases may be more interesting, and this is a popular mode of failure which we observed 24.1% of the times it fails because of forced termination condition, and most of these are due to the agent colliding with the scene objects. There was also this case where the object, once it's placed on the receptacle, doesn't stay stable and rolls off the receptacle. Finally, we have some early termination errors of skills. For example, the first nav skill here terminates early before passing on to the pick skill. So the pick skill starts. So there's some pick skill starts from a position where it can't basically pick any object, pick the object that it's supposed to pick up. So there's an issue of handoff here, which could possibly solve with the region goal-based reward, with which the top team proposed. So we conclude that basically our submission, the submission we made at that time, did not fully realize the full potential of using mobile skills, as the performance of 22%, 20 to 22% stayed behind the baseline that use stationary skills, and collision with scene objects seem to be a dominant mode of failure. Thank you, and let me know if there are any questions.
Yeah, I have a question. I think in the first failure case that you showed in the presentation, the agent was trying to move backwards towards the goal location, maybe because it has information about how far the goal location is with respect to the end effector. Do you have any ideas how you could solve that problem, that it like moves with its head facing forward, so it knows about the obstacle it's going to hit into?
So we could possibly, so I think the success criterion for navigation actually does have this condition that at the end it needs to face the object before it passes it on to the pick. So the successful nav does have this condition that eventually at the end it has to face the object, but we could have a reward that ensures that even from a distance, even from a sufficient amount of distance, it continues to look at the object. But yeah, it's because it has this geometric information. It doesn't care about looking at the object or using the visual observations for navigating.
What do you think about maybe de-incentivizing the backward actions?
Yeah, that makes sense. Yeah, possibly we could do that. Yeah, that sounds like a nice idea.
I have some experience with deep like navigation and learning navigation with backwards motion. For social nav, for example, you need to avoid dynamic obstacles like pedestrians. And in my experience, doing what Karma said and adding a penalty for backwards motion helps a lot. You don't have to prohibit backwards motion, but it'll lead to behavior where the robot will only move backwards if it absolutely needs to. And the rest of the time, it will focus on moving forward. And the other thing that you can also do in terms of crafting a reward function to kind of avoid this type of behavior is also just a constant penalty if a collision does occur, given that it won't violate this forced termination condition. That also helped a lot with navigation. I think back a few, maybe a year ago, when we were using habitat without with and without sliding, where the robot would get stuck on a wall if it collided, adding that penalty helped a lot to teach the robot to avoid any contact with the wall. So whether sliding was on or off, it helped ensure that no collisions occurred too. So yeah, just penalize backwards motion and collisions, I think is a good idea.
Yeah, a combination of them would definitely help prevent this behavior.
Yeah, I agree with like Naoki. I'm not sure how to pronounce your name. Yeah, I agree with
That's
his
good.
opinion. I think in my solution, I find that like adding collision penalty is the best way. I mean, for the best, I mean, it's get rid of some heuristic I need to design. I mean, just need to add some penalty constraints. And I think the robot can learn, like, because I mean, it's visual based, so it can try to first move forward to have some space to turn around instead of like here, like directly with the backward things. So it's, I mean, it's more, I mean, how to say, I mean, I hope to see like, I mean, adding collision penalty, yeah, it can lead to a more intelligent behavior instead of, I mean, if I directly disable the backward, I think the motion will be like very natural. Yeah. Yeah, it's just my opinion.
Yeah, I did have a few penalties based on the force that the agent executes, but I think they have to be tuned better to make this to prevent this behavior. But yeah, thanks. I'll work on making this better.
Okay, thank you. Yeah, we should probably move on now. So first, we will hear from our first invited speaker, Franziska, who is a research scientist manager at Meta. And then that'll be 30 minutes. And after that, we'll have a 10-minute break before moving on to our other speakers and then the object nav results after that. So, yeah.
All right. Thank you for inviting me. I'm excited to give a talk here. And this is a new project that I'm going to present today. So I'm very excited about hearing from you guys about what you think. Right. Can you see my slides?
Yep.
Okay, cool. So today I'm going to talk about a large-scale effort that that I'm leading at Meta, which we call Visual Cortex towards a foundation model for embodied AI. And specifically today I'm going to focus on a visual foundation model for embodied AI. Okay. I think we've all heard about foundation models in computer vision and natural language processing applications. And then some of us have already even today presented on foundation models for embodied AI. We want to basically pre-train a task agnostic visual representation with some pre-training objective, usually a self-supervised pre-training objective. And then we'd like to use that pre-trained model on a set of downstream tasks. And in this case, it's a set of downstream tasks that are either simulated agents or real robots. Where are we with this effort, right? There's a lot of excitement right now in this area. We see a lot of different efforts. We see like the R3M effort from an OVRL effort from Meta. We see the master visual pre-training for motor control from our Berkeley colleagues, and many more that I haven't been able to put on the slide right now. So we have a lot of excitement in this direction. But the current efforts are somewhat fragmented. We have previous pre-training algorithms. We all evaluate on different downstream tasks. We use different approaches for how to train the downstream tasks. That might be imitation learning, reinforcement learning. We might be using the pre-trained representations in frozen mode, or we might be fine-tuning them in the downstream task. And so as a result, all these results that we're seeing, these evaluations are not really comparable. And so we don't have a very clear picture of where we are with these. Where are we with the foundation model? How can we already train a foundation model that can succeed for several embodied AI tasks? Because ultimately, that's the goal of a foundation model in embodied AI, right? We want to be able to train and release model weights that serve as a backbone for nearly every research project in embodied AI and robotics. That's sort of the goal of a foundation model for embodied AI, and that's the goal we've set for ourselves in our effort. All right, so I'm going to talk a little bit about the methods that we're investigating, and then I'm going to present some very initial results. And I think I'm going to skip the next steps today. Let's see. Okay, so our very first milestone is that we want to have a comprehensive evaluation of current visual representation learning algorithms for embodied AI. And thus far, we've considered two pre-training data sets, HGSP and Ego4D. HGSP is a mix of navigation data from Gibson and HM3D. And then Ego4D is a huge data set of everyday tasks, partially annotated with language. We then look at several visual representation learning algorithms, namely autoencoders and variations of those, and then time contrastive methods. We also look at various policy training algorithms, imitation learning and reinforcement learning, and we do study both frozen and fine-tuned representations. And then in the evaluation, our evaluation benchmarks, our downstream tasks are a combination of habitat tasks, Mujoko tasks like DM control, Adroid, and MetaWorld, and we also include the tri-finger benchmark tasks. So we have a mix of navigation and manipulation. All right, just to give a little bit of an overview of how we are using the pre-trained visual representation, we take the current visual observation, we pass it through the pre-trained encoder that gives us a latent representation. That latent representation is passed into the policy, which then predicts action. Right now, we're considering frame level encoders, image encoders only. And as I've mentioned, the policy is trained with reinforcement learning or imitation learning. Now I'm going to go into detail, a little bit more details in the pre-training methods we're considering, and then I will give an overview of the evaluation tasks. Okay. We have sort of the pre-training methods that we've are considering are all frame level encoders, as I've just mentioned, but you can still inject temporal information when pre-training these representations. And so we have sort of made a distinction between that. So we have frame level encoders that were trained without temporal information, like master autoencoders and MVP. And then we also have a frame level encoders that were trained with temporal information, for instance, by using the temporal axis in the loss. So you use multiple frames in the loss. And these are R3M, VIP, and a method that we're working on, TMAE, which I'm not going to talk about today. We also are considering, but not developing right now, but existing, there are multi-frame encodings out there that basically just take the whole video and encode this into one. This is not something we're developing, but we are taking one of these representations that have been put out there and are including it into our downstream task evaluation. The pre-trained visual representations are VAT-based backbones. We are not going to make any drastic changes to the architecture at this point, so we're just going to consider the default VAT-based backbones. And again, this is the overview of the methods we're considering, a mix of MAE-based and time-contrastive methods, where some of them use temporal information and some of them don't. The masked autoencoder methods, for everyone, I assume everyone knows masked autoencoders, so I'm going to go very light on this right now. But just to give you guys an overview of who actually uses masked autoencoder methods, it's basically one of our methods that we're presenting is going to be masked autoencoder based, but then also off-the-shelf baselines that we're considering are MVP, which have been trained, has been pre-trained on ImageNet, Epic Kitchens, something, 100 Days of Hands, and Ego4D. And then our Omni MAE baseline also is based on masked autoencoder and has been pre-trained on ImageNet and something. The time-contrastive methods that we're considering, R3M, they are explicit. So R3M explicitly uses the video data, basically the multiple frames in the loss. So it's explicitly time-contrastive. And it uses also additional signals from language. So it's a video language grounding and a L1 penalty. We also consider VIP, which is a recent method that came out with, which is implicitly time-contrastive, and it uses goal-conditioned value function learning. All right. For the downstream tasks, our guiding principle was that we want to, because our goal is to pre-train representations that can work, if possible, on all embodied AI tasks and robotics tasks, we wanted to consider a very diverse set of embodied AI tasks in our benchmark. So one of the first things we did is actually pull together all of these tasks in one repository and have now in evaluation on all of these tasks, basically. And these tasks include some of the habitat tasks like image nav, object nav, and the mobile rearrangement tasks, adroit dexterous manipulation tasks, the deep mind control suit, and then the tri-finger manipulation benchmark, which uses the tasks that were presented at the NeurIPS Real Robot Challenge, like pushing the object and reaching the object, and things like that. So each pre-trained representation that we're considering is evaluated on all of these tasks. All right, I now have a very dense initial results slide. But before I go into this, I just wanted to present the protocol. We are pre-training a model. For each pre-training method we're considering, we're pre-training the model on both data sets. So we have two models and then a combined data set, which combines both of these data sets. We train either a policy via reinforcement learning or imitation learning on training tasks, which are either demonstrated tasks if we have demonstrations, or if we use reinforcement learning, we just have a set of training tasks specified. And then we evaluate the policy finally, both on the training tasks. So the final policy, we evaluate both on the training tasks and on new unseen test tasks. Because I'm presenting all of these results at once, the slide is void, sort of. Just to give you an idea of what kind of questions we're asking, here's a quick overview. Some of the questions are related to what's the impact of the pre-training algorithm? How important are like the different SSL objectives, for example? What's the impact of the data set and how does this vary with the tasks that we're looking at? And what is the impact of freezing versus fine-tuning? All right, this is the very dense result slide, so bear with me. The top two plots are, just for reference, higher is better. So these are success rates. The lower plot is lower is better. This is sort of the distance, the final distance in centimeters to the goal of a pushing task on try-finger. This left top plot is on habitat image nav at this point. And the dark blue and the light blue are frozen when we use the representation in frozen and when we use the representation in fine-tuned. And all of the results I'm showing right now are on the final test, unseen test tasks. Okay. So what's the impact of the pre-training algorithm? As we can see, the pre-training algorithm does matter. We do get different results depending on what pre-training algorithm we use. I would say the predominantly good method that we've tested across all of them, across all of the different variations, also the existing pre-trained methods, is actually masked autoencoder. That is kind of the first sort of insight we're gaining. R3M seems to also be performing fairly well on average. Then the impact of, let's first talk about the impact of freezing versus fine-tuning. We see very different results here, and we're still sort of disentangling these results. As you can see on Habitat, which uses reinforcement learning as a downstream task learning method, when fine-tuning, we see an increase in performance as compared to when using the frozen representation without fine-tuning. So if, as we're learning the downstream task, we're fine-tuning the representation, we can improve the results on the test tasks. This is not true when we look at DM control, which, by the way, uses imitation learning. Here we're using imitation learning as a downstream task learning method. And one of the questions we're wondering right now is whether this has to do with imitation learning more so than with the benchmark, or how much one, or whether the difference is that Habitat is visually much more challenging than DM control, and we're now, when we do imitation learning on the training tasks and we're fine-tuning the representation, we're basically overfitting. It's could be a combination of both. but yeah, that's one of the kind of results that we see right now. On the tri-finger, we actually see sort of not a big difference when fine-tuning. We see some slight improvement, but not as significant as we see. Actually, we see a slight worsening most of the time. So more closely to DM control. It's just not as significant as DM control. For tri-finger, we also use imitation learning. Okay. And then finally, the impact of the data set has been something that is interesting, and we see some interesting signals. When the HGSP dataset, we could consider an in-domain dataset for habitat, for the habitat task. And in fact, when we use it and fine-tune the representation, that is the best performing result we achieve when we pre-train MAE on HGSP. However, when we go into frozen mode and we don't fine-tune, what we actually see is that the combined dataset of Ego4D, which is a completely out-of-domain dataset, combining it with HGSP gives us the best performance. Most notably, this performance is better than taking a random VAT-based model and fine-tuning it on the task. So our pre-trained representation can outperform a from-scratch learning algorithm in this case. We do not quite see the same result on DM control, but what we do observe is that combining the data sets is not hurting as much. So basically, none of the data sets are considered in domain for DM control, so they're all out of domain. Combining data sets is not reducing the results a lot. And then on tri-finger, we do see a similar trend as on habitat, that combining data sets actually improves results when we stay in frozen mode. It's not true when we're fine-tuning. All right, so my takeaway here, one of the more interesting results here is that if we use our pre-trained representations in frozen mode, and if we pre-train them on diverse data sets, our frozen representations do better. And that is true for several of our downstream tasks. Okay. These were some initial results. It was a lot of data. Please feel free to ask questions. A quick summary of what I've just presented is that I've just presented some very initial results of the largest pre-training study to date. And we're in the works. Basically, just to give you a sense, I didn't show all the results we have because it's just too much, but we basically evaluated 20 plus downstream tasks on more than 10 pre-training methods and 3 pre-training video data sets. And we're in the process of adding more pre-training data sets, even more tasks. We're on track for 50 downstream tasks. And we are considering several hypotheses right now for improving our results further. The goal is that we release a pre-trained model that performs on par or better than from scratch training on diverse set of downstream tasks, and we're on track for that too. And we are planning to open source and release our code and models soon, so stay tuned. And this was obviously a team effort. A lot of work has gone into what I've already presented to you and what we're working on right now. So this would have not been possible with everyone on this slide. So thanks for listening. And yeah, let me know if you have any questions.
Thank you. Yeah, anyone can unmute and ask questions now. Maybe I can get started then. Did you guys on the results compare to from scratch? Sorry, the random visual encoder on the DeepMind control suite and the tri-finger task?
Yes, we also do have the from scratch by I guess I didn't have it in the plot. But
Is it a similar gap to what is in the habitat tasks?
it's a similar gap, yes. From scratch learning does worse than, I guess that's a good question. I don't, so basically for Frozen for sure it does much worse, right? Because
Yeah.
it doesn't have any visual information, but you can I'd have to check with Aravind, but I think on the DM control suite, he does have results where the fine-tuning can achieve on par performance than the pre-trained Frozen representation.
Mhm. Makes sense.
I have a question.
Yeah.
Are you also seeing how much the downstream training becomes faster with different pre-training methods? Are you seeing the sample efficiency?
We have some very early signals on some of the tasks so we didn't track this from the beginning, but we are now. And on Habitat, from what I remember from reading this week, it was kind of like 4 to 5 times faster. This is in compute. So I can't recall right now in terms of sample efficiency, but we do see some sample efficiency improvement. But yeah, that's a very good question, and we are planning to add this to our analysis.
Cool.
I do think that even, so this is a debate I don't know, I'm curious to hear everyone's thought, but that's a debate we've been having is, in my mind, even if the pre-trained representation didn't give you all of these benefits, but I think we're already seeing some of these benefits, but even if it didn't, being able to hand out these pre-trained representations and everyone just being able to start from that pre-trained representation, like I'm imagining robotics students who don't necessarily have a background in how to train visual representations, and just being able to start with this and do imitation learning, which is very doable. I think this is amazing. So for me, being able to share pre-trained representations and helping students get started, or even other researchers get started in embodied AI or robotics without having to learn about or becoming an expert in reinforcement learning with visual representations, I think that's pretty amazing. So yeah.
Yeah, I totally agree. I think it's incredible that there's consistent findings between these very diverse tasks, and certainly it's a great, starting point for to distribute to people. One thing that I'm really interested in is kind of the nuances between, for instance, like the effect of data set or pre-training strategy across the different tasks. Especially think that like the fine-tuning thing on DMC is pretty interesting. To test that hypothesis of like the supervised learning, is there another task where you guys use supervised learning as opposed to RL fine-tuning? And do you guys see a similar conclusion there?
So actually tri-finger and DM control are very similar in the sense that they are visually not as challenging as Habitat, and we both use both of these results use imitation learning, so behavior cloning. And on tri-finger, we don't see this massive drop when fine-tuning. So Aravind and I have already been discussing this result because it's interesting. One major differences is the type of control we're using at the lower level. The tri-finger uses end effector control, so high-level control, and that's the policy is learned at a more high level than for DM control. So in tri-finger, the the policy that we're learning based on the visual representation commands end effector positions at a way lower frequency than the M control, which commands torque commands. And yeah, we are wondering if basically the dagger effect is much stronger in the M control, where the error accumulation is much worse because of the more fine-grained control, the time steps are much more, basically. And but also probably the visual, like minor visual differences make much more of an effect. Unclear, but this is our hypothesis right now.
Sure, thanks.
All right.
Yeah, so if anyone has any more questions, probably have time for one more. Okay, if not, then we can take a break now for 10 minutes. And then once we come back, we'll hear from our next speaker. And yeah, I guess we'll resume around 2:30. Okay, yeah, no questions, then we'll take a break now. Thanks.